My name is John Baneri. As a dedicated mechanical engineering student with a passion for the aerospace industry, I am constantly exploring the intersection of innovation and technology. My academic journey has equipped me with a strong foundation in engineering principles, while my hands-on experience in aerospace projects has deepened my understanding of complex systems and design challenges. I am particularly fascinated by aerodynamics and propulsion, and I thrive on the opportunity to contribute to cutting-edge developments in aircraft and spacecraft design. Beyond my studies, I enjoy engaging in activities that fuel my curiosity and creativity. Whether it's coaching my son's baseball team, writing music on my guitar, experimenting with 3D modeling software, or keeping up with the latest advancements in aerospace technology, I'm always eager to learn and grow. This project is about the stress and strain of the parts of a reciprocating piston engine under operation. Reciprocating piston engines are one of the most important technological developments in human history. They are used in many applications, most commonly in personal automobiles. Real engines consist of many moving and static parts, but this study concerns itself with four main parts that are typically referred to as the rotating assembly, which are the pistons, piston pins, connecting rods, and crankshaft. This project examines the parts as if they were operating under similar conditions as combustion engines in personal automobiles. An engine experiences peak cylinder pressure in the combustion/power stroke and can typically reach 1,000 psi, or about 6.895 megapascals, for commercially available engines at full load, to 1,500 psi, or about 10.3 megapascals, in engines for racing applications. For the analysis of our engine, we used 8.5 megapascals, which when converted to force using the top area of the piston, is approximately 54,074 newtons, which we moved up to 54,200 newtons to put the parts under more difficult conditions. Under this force, we analyze the parts under their worst condition, which is typically when the piston is either at bottom dead center or top dead center. At that moment, if combustion were to occur, many parts would experience the worst possible conditions. In real engines, however, combustion does not output its full force at top dead center, since there is time between the ignition and the expansion applying pressure to the top face. Furthermore, the connecting rod was analyzed under buckling and bending. Bending in the connecting rod occurs when the connecting rod reaches its maximum offset from the vertical axis. In this project, we analyzed the rotating assembly of a reciprocating piston engine. We analyzed the piston under compression based on the pressure of combustion being supported by the piston pin. The piston pin was analyzed under bending, being supported by the connecting rod, and the force being transferred from the piston. The connecting rod was analyzed under compression, buckling, and bending conditions. The force was applied through the piston pin into the small end of the connecting rod, and the rod was supported at the large end by the crankshaft. For compression and buckling, the connecting rod is analyzed when the piston was at top dead center. For bending, the connecting rod is analyzed when the crankshaft is 90 degrees offset from top dead center, leading the connecting rod to no longer be parallel to the force from the piston. The connecting rod is approximately 13 degrees off the vertical axis under the bending condition. The crankshaft was analyzed under two conditions, bending and torsion. For bending, the crankshaft was analyzed with the piston at top dead center, and for torsion, the crankshaft was analyzed 90 degrees off of top dead center. For the design optimization, the piston was optimized to reduce weight while maintaining its minimum factor of safety. To do this, the inner diameter of the piston was varied from 82 mm to 87 mm in 0.5 mm steps, with it originally having a diameter of 85 mm, and allowed for cast carbon steel as a material variation. SolidWorks determined that, based on the weighting of the goals, the ideal inner diameter was 87 mm, and the ideal material between cast carbon steel and alloy steel was alloy steel. The last section is the thermal analysis of the piston, both at steady state and transient. Using a convection coefficient of 293 watts per square meter per Kelvin, the ambient temperature for the top face was set to 1,193 Kelvin, with all other exposed surfaces having an ambient temperature of 293 Kelvin. The max steady-state temperature was 536.7 Kelvin. The transient analysis 525.6 Kelvin after 300 seconds. Recommendations for future analyses could be analyzing the engine block under the pressure of combustion in the combustion chamber, analyzing more variation in material for more parts, and optimizing more parts for an improved system. This concludes our presentation. Thank you for watching.